AI diffusion models deep dive. How senior engineers master generative modeling with score-based methods in modern AI systems. Welcome back to Agentic AI World, the daily show where senior engineers talk shop about real AI systems. I'm your host, and today we're diving deep into diffusion models. If you've used DALL-E, Stable Diffusion, Midjourney, or Sora, you've been on the receiving end of diffusion models. Understanding how they actually work under the hood is becoming essential interview territory, especially for roles at AI labs, generative AI startups, and any team building image, audio, or video generation systems. So let's get into it. What is a diffusion model? A diffusion model learns to generate data, images, audio, video, by learning to reverse a noise-adding process. Here's the intuition. Start with a real image. Add a tiny bit of Gaussian noise. Add more noise. And more. After around 1,000 steps, you have pure random noise. The image is completely destroyed. A diffusion model learns the reverse of this process. Given noisy data, predict what the original looked like. And importantly, it does this step by step, removing a little noise at each step until you recover something coherent. This reverse process is what you use at inference time. You start from pure noise, and the model iteratively denoise it into a realistic image. Simple concept. Staggering results. The two phases. Forward process, also called the diffusion process asterisk. You take real data and progressively corrupt it over T time steps by adding Gaussian noise. By the time you reach step T, the original data is unrecognizable. This process is mathematically defined, no parameters to learn, just a fixed schedule. Reverse process, also called the denoising process asterisk. This is what the neural network learns. At each time step T, given the noisy image and T itself, the network predicts either the original image, the noise that was added, or the score function, the gradient of the log probability of the noisy data. Different formulations, same underlying mechanics. In practice, DDPM, denoising diffusion probabilistic models, the landmark 2020 paper, predicts the noise. And it works extraordinarily well. The training objective. Here's the beautifully simple loss function. At each training step, you sample a random image, pick a random time step T, add the corresponding noise to the image, and train the network to predict that noise. Mean squared error between the predicted noise and actual noise. That's it. One loss function. Thousands of time steps sampled uniformly. And yet this produces models that generate photorealistic images. The network is typically a U-Net architecture with time conditioning. The U-Net has an encoder that compresses the image and a decoder that reconstructs it, with skip connections in between. The time step T is embedded and injected into every layer via sinusoidal encodings, the same trick used in transformers. Attention layers are added at lower resolutions in the U-Net to capture global structure. Self-attention at 16 by 16, 8 by 8 resolutions. Convolutions everywhere else. Noise schedules. The noise schedule defines how quickly you go from clean data to pure noise across T steps. Linear schedule asterisk variance increases linearly. Simple, works reasonably well. Cosine schedule asterisk introduced and improved DDPM. The image stays recognizable for longer before degrading fast near the end. Better for images. DDIM schedule, from the Elucidating the Design Space of Diffusion-Based Generative Models paper, treats noise level as a continuous parameter and is used in many state-of-the-art systems. For interviews, know that the schedule affects training dynamics and sampling quality. A bad schedule means the model spends too much capacity learning noise patterns that aren't useful. Sampling, the tricky part. Training is cheap. Sampling is expensive. DDPM sampling requires 1,000 denoising steps. At each step, you run a full forward pass of the U-Net. For a 512 by 512 image, this can take 30+ seconds on a modern GPU. That's unusable for real products. Enter DDIM, denoising diffusion implicit models. DDIM reformulates the reverse process as a non-Markovian process, allowing you to skip steps. Instead of 1,000 steps, you can get acceptable quality in 50 steps, or even 20. This is a 20x to 50x speedup with minimal quality loss. For production use, Stable Diffusion, Midjourney's internals, accelerated samplers like DDIM, DPM Solver, and Euler-A are standard. You pick your sampler based on quality-speed trade-off. For interviews, if someone asks how you'd optimize a diffusion pipeline, the answer starts with sampler selection and step count. Latent diffusion models. This is where Stable Diffusion lives. Running a UNet on full 512 by 512 pixel images for each denoising step is expensive. The key insight: you don't need to diffuse in pixel space. You can diffuse in a compressed latent space. Latent diffusion models, introduced in the LDM paper, work like this. First, train a separate VE, a variational autoencoder, to encode images into a 4 by 64 by 64 latent space. 8x compression in each spatial dimension. Then, run your entire diffusion process in that latent space. The UNet is 64x smaller. Training is 4x to 8x cheaper. Sampling is proportionally faster. To get the final image, you decode the denoised latent back through the VE decoder. Stable Diffusion is a latent diffusion model with a clip text encoder for conditioning. That's the core architecture powering hundreds of consumer products. Conditioning and control. Unconditional generation is cool. Conditional generation is what products need. Text conditioning *, you embed the text prompt using a clip or T5 encoder, then inject those embeddings into the UNet via cross-attention. Every spatial location in the feature map attends to the text tokens. Classifier-free guidance * at training time. 10 to 20% of the time you drop the text conditioning and train unconditionally. At inference, you run 2 UNet passes, one with the prompt, one without, and interpolate. Output equals unconditional plus guidance _ scale *, conditional, unconditional. Guidance scale controls how closely you follow the prompt. Higher scale, more adherence, more saturated, less diverse outputs. Typical values, 7 to 12. ControlNet * a technique for adding spatial conditioning, depth maps, edge maps, human poses, by fine-tuning a copy of the UNet encoder on paired data and injecting learned residuals. This is how you get post-controlled generation. Score-based generative models. At a deeper level, diffusion models and score-based models are the same thing. Score functions are the gradient of the log probability density of the data. If you know the score function, you can sample from the distribution using Langevin dynamics. Start from noise, follow the gradient of log probability toward high-density regions. The connection: training a diffusion model to predict noise is mathematically equivalent to training it to estimate the score function. The noise predictor is the score estimator. This unification, formalized by Yang Song and colleagues in the NCSN and subsequent papers, gives diffusion models their theoretical grounding and explains why stochastic differential equations, SDEs, can describe both the forward and reverse processes continuously, not just in discrete t-steps. For interviews at AI labs or research-adjacent roles, knowing this SDE formulation shows deep understanding. Evaluation metrics. FID, Freshet Inception Distance * measures the distance between the distribution of generated images and real images in feature space. Lower is better. Standard metric for image generation quality. IS, Inception Score * measures both quality, sharp, recognizable, and diversity. Less favored now because it ignores real data distribution. Clip Score * measures semantic alignment between a text prompt and generated image. Essential for text-to-image. Human evaluation * for production systems. You almost always run user preference studies alongside automated metrics. FID doesn't correlate perfectly with human preference. Production considerations. A few key points for system design interviews. Latency * even with DDIM at 20 steps. A 512 by 512 image takes 2 to 3 seconds on a single A10G GPU. 4 sub-second requirements. You need model distillation, consistency models, or flow matching, which can generate in 1 to 4 steps. Throughput * batching multiple requests together amortizes the UNet overhead. You want to maximize GPU utilization, not minimize per request time. Safety filtering * all production diffusion systems run output through NSFW classifiers before returning results. Input prompts go through content filtering too. Not optional. Watermarking * Stable Diffusion and others embed imperceptible watermarks in outputs for provenance tracking. Memory * a loaded Stable Diffusion XL model uses 6-8 GB VRAM. For serving at scale, Quantization to int8 or fp8 cuts this roughly in half. Interview questions you should nail. How does a diffusion model differ from a GAN? GANs use adversarial training. Diffusion uses denoising. Diffusion is more stable to train, produces more diverse outputs, slower at inference. How would you reduce inference latency in a diffusion-based system? Faster sampler, DIM/DPM solver, fewer steps, latent space, not pixel space, model distillation, quantization, operator fusion, batching. What is classifier-free guidance and why is it used? See above. It improves prompt adherence without needing a separate classifier model. How does ControlNet add spatial control to a diffusion model? Copies the encoder weights, trains on paired condition image data, injects 0nv residuals back into the main UNet. What's the difference between DDPM and DDIM sampling? DDPM is Markovian. Each step depends only on the previous step, requires 1,000 steps. DDIM skips steps by treating the process as non-Markovian, achieving good quality in 20 to 50 steps. Wrapping up, diffusion models are one of the most important architectural innovations of the past 5 years. They've changed image generation, video generation, audio synthesis, and molecule design. Understanding them, from the noise schedule to the score function to the inference tricks, is the mark of a well-rounded senior AI engineer. Today you learned the forward, noise adding, and reverse, denoising processes. How DDPM trains with a simple noise prediction loss. Noise schedules, linear, cosine, EDM, DDM, and accelerated sampling. Latent diffusion and why stable diffusion is fast. Text conditioning via cross-attention and classifier-free guidance. Score-based model unification. Production constraints, latency, safety, memory. Tomorrow we continue our deep dive series. Subscribe so you don't miss it. This is Agentic AI World. See you tomorrow.